In the second talk of microstructure models and beyond, I will be presenting some of the microstructure models that are implemented in Dipy and show the code and how to process it. So for this, I will show some of tutorials that are available under my on my GitHub repository, Dipy Workshop 2021. Okay. So the first model that I will be talking is a white matter track integrity model. This basically is a two-compartmental model, and it has a special feature. So instead of trying to fit this two-compartmental model directly to do diffusion-weighted signals, it tried to extract these compartments using the diffusion tensor and kurtosis tensor. This is done because since the diffusion tensor can be extracted for fitting approach that have unique solution, the estimates from the white matter track integrity model avoids the problems of non-linear least squares fitting approach. To remove some of the degeneracies on the conversion between the kurtosis parameters and the white matter track integrity parameters, some assumptions are made on this model. So for example, the extracellular diffusivity on the axial directions is assumed to be higher than the intercellular axial diffusivity. And the radial diffusivities of the intercellular space is assumed to be 0. Although several studies show that this assumption should not be valid, this model shows to provide useful information on several different applications. So if you're more interested on this, I recommend you to give a look to this manuscripts, for example. It's also important to note that this model only takes into account one compartment per restricted and hindered diffusivity. So this can only represent well-aligned fibers. Okay, so I will show here the code. Okay. So the first thing that you have to do is, of course, loading your data. So here I'm loading it directly using the fetcher, so the get fnames function of Dipy. If you want to use your own multi-shell data on this tutorial, you just have to define your paths on these variables, okay? So as the tutorial of yesterday, you have to define the GitHub object that contains the information of your b-values and your gradient directions, okay? So then I'm here doing some pre-processing steps. So I'm masking the data, and also I'm applying Gaussian smoothing just to suppress some noise effects. Although here I'm just using a Gaussian smoothing, I recommend you that you use the more advanced denoising techniques that Shreyas presented yesterday. Okay, so also another thing that I'm doing here in the pre-processing step is defining the voxels that contains well-aligned fibers. And for this, I'm using the diffusion tensor fitted from the DTI model. And basically what I'm selecting is voxels in which the diffusion tensor looks like a linear geometry rather than a planar or a spherical geometry. This selection criteria was done similar to the original white matter track integrity paper. So for more information, you can also find there, okay? So after pre-processing, you can fit the white matter track integrity model. And this follows the same recipe as the models that I presented yesterday. So you have to call the right model from Dipy construct. In this case, is the DTI microstructure model. Define the model according to your acquisition parameters, and then you can fit your data, okay? After fitting, you can extract the model parameters, and here I'm extracting the volume fraction of the intercellular space, and the tortuosity, which is defined has the axial diffusivity and the radial diffusivities of the extracellular space. Okay. So I'm plotting here this values overlaid on the mean kurtosis map. And below, I'm showing also the histograms of the values. And this is just to show that we have similar range to the reported on the original paper. Okay. So the second model that we have in one of the a model that we have also implemented in Dipy is the spherical mean technique to compartmental model. In this, I represented the details on the previous talk. And so if you look to this manuscript, you will notice that there is a relationship between the SMT two compartmental models with the mean signal DKI model that I presented yesterday. So basically what we did in Dipy is we allowed to extract the spherical mean technique parameters directly from the fit of the mean signal DKI model. So I will show this here in the code. Okay, this is the second tutorial. So basically, you have to run the similar code that I presented yesterday for the mean signal DKI tutorial. So here I'm just loading the data. I'm fitting this mean signal kurtosis model and extracting, for example, the mean signal diffusivities and mean signal kurtosis, and I'm plotting them here. Okay, this is a standard mean signal DKI parameters. However, you can also directly extract the SMT2 parameters. So, for example, the axial water fraction of this model and the intersected diffusivity, which I'm plotting here. Okay, keep in mind that as I mentioned on my previous talk, you have to be very careful in interpreting the parameters of this model. So this should not be taken like a real microstructure model, but more as a phenomenological model. However, to point that this can also indeed be very useful. For example, if you look to the volume fractions extracted here, this might only provide index of non-Gaussian diffusion. So you can see that you have exactly the same contrast as a mean signal kurtosis. But now these values in opposite to the kurtosis values are ranged between 0 to 1. So this can be a very useful normalized quantity of the total kurtosis of your system. Okay. So the last model that I wanted to present here is the free water DTI. This is a very simple expansion of the DTI model in which you basically incorporate a free water term on the diffusion together with the diffusion tensor. And this was proposed, for example, if you want to remove the partial volume effects on studies, for example, aging, in which you have increase of this confounding factors due to the atrophies of the brain and the enlargements of the ventricles. Also, the estimation of the free water fraction, as shown in previous studies, might be useful as a biomarker to target different pathologies. Okay, so as this is a two-compartmental model, it requires information of multiple B values. However, it's important to note that some approaches have been tried to fit this using single shell data, using spatial regularization and initial guess with priors. This we explored this together with Mark Ullum and Rita Nunes, and this code is available here. However, it's to point that you should use this codes with care, because it can provide some misleading information. But advice on this are reported in this manuscript. Here, I'm showing the implementation of the multishell data, which should provide more accurate estimates. Okay, so I will show here in the tutorial. Here it is. Okay, so again, has the other microstructural models. This always follows the same recipe. So first, you have to download the data. So here I'm fetching another multishell data set that you can also download it from Dipy. I'm reading it and doing some mask. So fitting is usually is the same rule. So you have to define the free water DTI model from Dipy reconstruct, define it according your acquisition parameters. Then you can fit it using the fit function of the model object. So here I'm producing the FA and MD decoupled from the free water effects. And for reference, I'm also computing here the standard FA and MD from DTI. Okay. So here I'm comparing the two maps. So here is the FA maps. You can see particularly from if you subtract the free water DTI maps from the standard DTI maps, that the FA estimates are now higher from using the free water DTI because you remove these isotropic components of the free water. Okay. And yeah, so this is the same from the mean diffusivities. So here you suppress the mean diffusivities of the free water. And here is the map of the free water estimates, okay? The volume fraction of the free water. Okay. Then sometimes when you apply this model, you will observe high intensities of FA near to the ventricles. So you can see it here. And what I'm showing here below is a strategy to remove this large FA values because this might be caused by artifacts. So since near to the ventricles, you remove most of the signal because it only contains free water estimates, then the remaining signal can produce very high FA values. So to remove them, what I'm doing here is just masking out the values that were estimated to have a very high water volume fraction. And yeah, this is the models that I wanted to present today. Of course, there's many other models that I didn't have time to present, and also there are some models that we intend to incorporate in Dipy. So here is just some names. I only want to highlight a few promising strategies. So for example, we have here the Teddy model that uses the information also from different T2 acquisitions to try to improve the precision of microstructure model estimates. There's also an interesting work on how to more robustly estimate axon radii by Verrett et al. Another interesting model is the Sandy model that tries to improve the Spanish model and introduce a spherical compartment again on the models to try to modeling the summa fraction. So also very interesting work that you should give a look. And also mentioning here the advanced diffusion MRI sequence. So you can, has pointed here in this manuscript, you can use this information to try to improve also your microstructural model estimates.